Now let's talk about equations of planes. A plane, by definition, is the set of all points for which any vector, that's missing a little vector symbol up there, p0 to p is perpendicular to some specific vector n. Now this is pretty similar to the definition of a line, but there's some differences, so let's make sure we recognize what they are. All of the points that live in this blue plane, I'm going to call them P with a subscript. So there's infinitely many points in the plane. They could be called P0, P1, P2, P3, P4, etc., right? And between any 2 points in the plane, using P0 and whatever other point you want, you can make a vector. And I've got 3 of them demonstrated here for you. And the definition of the plane says that all of those red vectors, infinitely many of them that can be made in the plane, every single one of them is perpendicular to this vector n. We use the vector n to define the plane. Similar to how we used a vector to define the line, we'll use one for the plane, but this vector n has to be perpendicular to the plane, not parallel. We can see that here with the little perpendicular right angle notation. So to come up with an equation for a plane, I'm going to specifically talk about a general point P. Notice that this P does not have a subscript, and neither do its components x, y, and z. And that's because I am going to let that P be any point it wants to be in the plane. P0, on the other hand, that has subscripts, so I'm fixing that point. So I'm talking about a specific point P0. I'm talking about a general point P that satisfies the condition that the vector P0 to P is perpendicular to n. If these 2 vectors, P0 to P, are red vector, and n, the white vector, if they really are perpendicular, then we know that the dot product calculated from those 2 vectors has to be equal to 0. That's one of the ways that we checked to see if 2 lines are perpendicular. Calculate their dot product. Is it 0? Yes, then the lines are perpendicular, or the vectors are perpendicular. If the dot product is not 0, then we know that they're not perpendicular, but we don't know anything else beyond that. So we start with our perpendicular statement, and we turn that into the dot product between the red and white vectors. From here, we're going to replace the vectors with the component form. So from P0 to P, we'll replace that with the components. And then the vector n, I'm going to give those kind of arbitrary components A, B, C, and I'm picking those to be the components because that matches the textbook. Plugging in those components, we see that our dot product turns into this vector with all of its components dotted with the second vector. We're still saying that dot product equals 0. But then right after that, we're going to actually apply the dot product. So I'll take the first component from my P0 to P vector, and I'll multiply it to the first component of my n vector to get this term. And then I'll repeat that with the other corresponding components so that I can change my vector equation. This is a vector equation. We know that because there's vectors in it, and we can rewrite it as a scalar equation. Now from here, we can make this general definition for the scalar equation of a plane. Just like a line, we need 2 things, 2 pieces of information about the plane to be able to write an equation for it. We need to know the components of the vector n that the plane is perpendicular to, and we need to know the coordinates of any single point in the plane. And then we can plug those in. The components from the vector n become the coefficients, and then the point that we pick from the plane, we plug those coordinates into the x0, y0, z0. And technically, that's the scalar equation of a plane. Often though, once we plug in those numbers, we like to clean things up and simplify. So after we've plugged everything in, we will simplify so that we have the variable terms on one side. So after we multiply and distribute, combine like terms, yada yada, we'll have ax plus by plus cz. We'll leave those terms on the left. All of the other terms, like when I multiply a times negative x0, b times negative y0, and c times negative z0, I'm going to move those over to the right-hand side, and after adding those up, I'm going to call it d. So the simple scalar equation of a plane has the variables on the left and a single constant on the right. Let's go ahead and try some. So our first example says to find the equation of a plane that passes through the given point, 1, 4, 3, and contains the line that's described by this symmetric equation. So this takes a little bit of thought. So let's think about what we have here. We know that the equation of a plane, we plug our values into this scalar equation. We know what to plug in for x0, y0, and z0. Those would become 1, 4, and 3. So let's go ahead and write that out, what we have so far. The only thing that's stopping this from being finished is the fact that we have A, B, and C still in a general form. We want to find out what numbers belong there, and then we'll be done. So to do that, we need to find a vector n that is perpendicular to the plane. Now, we're not given that, but we are given enough information to find it. If we imagine that this is a plane, and that this line is contained within that plane, then we could picture that the line is laying on top of or inside of or is part of, it's contained by that plane, which means the vector v that that line is parallel to also lives in the plane. That's not the vector n that we want. We need a vector n that is perpendicular to our plane. So what we'll have to do is find that n through a bit of a convoluted process. We have the vector v from the line. So let's extract that. V from the line looks like 1, 2, 1. We need another vector inside of that plane so that we can cross the two vectors from the plane to find the vector n. To generate another vector in the plane, all we need to do is generate another point, and we could find the vector between 2 points. So looking at my symmetric equation, I want to find another point other than 1, 4, 3, so that I can create a vector between the point 1, 4, 3 and the new point that we're creating. Remember that this is equal to some parameter. I'll call it t. So if I pick a value for t, I'll be able to find x, y, and z. If I pick t is equal to 0, then I can separate this into 3 equations. One where x is equal to 0, one where y minus 1 over 2 is equal to 0, and one where z plus 1 is equal to 0. And there's nothing special about 0. I could have picked any number for t that I'd like. But I like 0. It's an easy number to work with. So I would get x equals 0, y would have to be equal to 1, and z would have to be equal to negative 1. So using this point that we just found, 0, 1, negative 1, and the point that was given to us, 1, 4, 3, we can generate a new vector. I'll call it w. And it doesn't matter which one's the initial or the terminal, so I'll call this my terminal point and this my initial point. So I'll have 1 minus 0 for my x component, 4 minus 1 for my y component, 3 minus 1, sorry, minus negative 1 for my z component. That's my second vector. So we're going to find a vector n that's perpendicular to the plane by crossing the vector v from the line with the vector w we just created using 2 points in the plane. We'll use our 3 by 3 matrix to calculate that. Now that we've found the vector perpendicular to our plane, we can use those to find A, B, and C. Plugging that into our scalar equation, I'm just going to replace A with 5, replace B with -3, and replace C with 1. And then I'm going to clean that up a little bit. So I need to erase my beautiful artwork. And I can distribute this. Combine my like terms, all the constant terms. And then I'm going to move the constant over to the right side. And that is the final answer for my scalar equation of a plane.